And okay, so Bismillah ar-Rahman ar-Rahim. Okay, so let me tell you guys the paper layout first. Okay, how stuff is gonna work in A2 chemistry. Okay, so basically, A2 chemistry 9701. All right, so this is the paper pattern. This is the paper pattern. We have a paper 4 and a paper 5. Paper 4 is the major paper. It's the paper that has the greatest weightage in your grade, in your A-level grade. Okay, approximately like 40% of your grade, of your A-level grade depends upon this paper. Why? Because it has the greatest number of marks, okay, 100 marks. And 2-hour time period and 8 to 9 questions are there. These are the questions similar to your paper 2 in AS, which you did in AS, okay, but a bit more difficult. Okay, the difference is that they are a bit more extensive, a bit longer. That's why the time period is also greater. Okay, and threshold is also pretty good. So basically, this is the major paper where you are gonna focus your strengths. Paper 5 is a paper that is similar to paper 3. Okay, it uses the knowledge of P3. Remember P3, the practical paper, the knowledge of P3 is applied over here. It is applied in paper 5. Okay, the knowledge is applied in paper 5. So knowledge is going to be a paper-based question paper, or 2 to 3 questions are there, and 30 marks paper is going to be 30 marks, and 1 hour and 15 minutes is the time period given. Right? Let's move on. Okay, now a few this syllabus outline. Okay, we have energetics. In energetics, we are going to do the Born-Haber cycle, group 2 chemistry, entropy, electrode potentials, kinetics, equilibria, having all these constants in it. Okay, Kc, Kp, these are the ones which you've already done in AS. Ka is also an equilibrium constant of acids. Kb is an equilibrium constant for bases. Kw is an equilibrium constant for water. Ksp is also an equilibrium constant. Kpc is also an equilibrium constant. Buffers, pH calculation, and all this stuff is going to be covered in great detail in this chapter, equilibria. And then we have polymers, inorganic chemistry, which has transition metals, and group 2 chemistry. Again, certain part of group 2 lies over here in inorganic chemistry, and pretty much of it is similar to the AS chemistry. So you guys should have a firm grip of your AS inorganic chemistry for your A2 or inorganic chemistry as well. Okay, then we have our organic. The first chapter is benzene, and then nitrogen compounds. This is something very similar to the stuff that you've done in your O-levels, the amides you've done in O-levels, and amino acids. This is going to be relatively new, and acyl chlorides is going to be new for you guys. Carboxylic acids you're familiar with, polymers, and then condensation polymers and addition polymers and stuff like that. Then we have analytical chemistry, in which we have the infrared spectroscopy, mass spectroscopy, and then proton NMR, carbon-13 NMR, chromatography, electrophoresis, and then KPC. KPC is an equilibrium constant, again, which is actually used over here in separation techniques. Okay, this is also something that we are going to look at in great detail later on. Okay, so this is basically the entire syllabus of A2. Okay. It looks as if it's quite small, not too extensive, but trust me guys, this is far more extensive than your AS, okay? So we'll need a lot more dedication and hard work in order to complete this in time along with the past papers, okay? And guys, in A2, we are gonna do past papers at the end of each lecture, at the end of each class, I mean at the end of each chapter, because we've got enough time to cover past papers alongside the syllabus as well. Okay. Now, yes, topical. All right. So now today's topic. Moving on to today's topic, energetics. Basically, lattice energy. Okay, this is something new for you guys. Okay, it resembles the AS chemistry topic of Hess's cycle, Hess's law. So you are gonna need the knowledge of Hess's law over here. Remember Hess's law? It was an energy cycle which was used to calculate the enthalpy changes of reaction, which were actually not possible under lab conditions. Okay, so basically this chapter deals with knowledge from that chapter. Now, some important terms and important definitions that you guys are supposed to know from AS, of course. before you can do this chapter. Okay, now the first definition is enthalpy change of formation, or I should rather say delta HF naught, standard enthalpy change of formation. Okay guys, do you remember the definition of standard enthalpy change of formation from your AS knowledge? It is actually the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions of 25 degrees Celsius, 1 atmospheric pressure, and 1 mole per dm cube concentration. All right, so this is basically the enthalpy change of such a reaction is going to be the enthalpy change of formation of this product of NaCl in this case. Okay, so this is something you've done in AS. So what if I had a reaction like this, magnesium reacting with chlorine, and magnesium is a solid and chlorine is a gas, which these are the standard states under standard conditions. So they'll give you MgCl2 solid, right, under standard conditions of 25 degrees Celsius, 1 atmospheric pressure, and 1 mole per dm cube concentration. When the concentration doesn't apply over here because we don't have solutions, but see, 1 mole of the product is formed. So again, the enthalpy change of this reaction is also going to be the enthalpy change of formation of magnesium chloride, MgCl2. Now, if we had two products on the product side, if we had 2 moles of the product, then the enthalpy change of that reaction would have been twice the enthalpy change of formation of magnesium chloride. In both the reactants would have doubled as well, and so in this case the enthalpy change of formation is the enthalpy change of this reaction is gonna be twice the enthalpy change of formation, right? So guys, is enthalpy change of formation revised? Is it clear? Please confirm so that I could move forward. Hussain?
Yes, sir.
Right. All right, I'll repeat the last part. Basically, over here, I just told you that if, let's say we've got magnesium reacting with chlorine, forming magnesium chloride, okay? And enthalpy change of this reaction is going to be enthalpy change of formation of magnesium chloride, okay? This is what you already know. But if I multiply the entire equation by 2, that would mean that we've got now 2 moles of the product, okay? 2 moles of the product. 2 moles of the product would mean that the enthalpy change of this reaction is going to be twice the enthalpy change of formation of magnesium chloride. So this is what I was telling you, because it is actually the enthalpy change when 1 mole of a compound is formed from its elements in the standard states under standard conditions. Hassan, do you get this now? What we have 2 different compounds? No, actually for 2 different compounds we cannot have enthalpy change of formation actually. Okay, if we have 2 different compounds, then no, sorry. Okay. Only we are gonna deal with situations in which we have only 1 compound, or we are gonna deal in situations in which we are gonna label the enthalpy changes with respect to that compound. Okay, we are not gonna have 2 compounds in such stuff. Now, enthalpy change of atomization, this is also something you've done in AS, and I should rather say standard enthalpy change of atomization. If this is the standard enthalpy change of atomization, then that would mean the reaction is performed under standard conditions. Okay, standard conditions you guys already know, at 25 degrees Celsius, 1 atmospheric pressure, and in case of solutions, the concentration of 1 mole per dm cube. Anyways, these are the standard conditions. Now, what is enthalpy change of atomization? Enthalpy change of atomization, as the name suggests, atomization, atom. So the enthalpy change when 1 mole of an atom is formed from its elements in the elements in the gaseous state. Okay, 1 mole of gaseous atoms are formed. 1 mole of the gaseous atom, if is formed from its element under standard conditions, but the element must also be in the gaseous state, the enthalpy change of that reaction is going to be the enthalpy change of atomization of this compound, that of this element, of this atom that has been produced. Okay, in this case chlorine. Okay, so now this is enthalpy change of atomization. So for example, if I had magnesium solid, okay, And now if this magnesium solid, okay, if this, guys, let me correct myself. This element is not always necessarily in the gaseous state. Okay, it can be in any standard state. It can be in its standard state. Okay, it has to be in its standard state. If, for example, in this case, chlorine is a gas, magnesium is a solid, but the product that we get must be an atom, a separate atom, and must be gaseous in nature. Okay, for example, over here, if magnesium solid, if we heat it, provide it some energy, it will produce magnesium atoms, okay, in the gaseous state. Can any one of you tell me what forces are being overcome in this reaction? What forces are we breaking in magnesium solid to convert it into magnesium gas? Hussain? Any idea?
No, sir.
Actually, this is a metal. Hassan, this is a metal. So it contains metallic bonds. We are breaking metallic bonds. Okay? Not the intermolecular forces. Intermolecular forces exist only in molecular compounds. Okay? In this case, again, we've got 1 mole of an atom produced, and from its element in its standard state under standard conditions. So again, the enthalpy change of this reaction is going to be the enthalpy change of atomization of magnesium. Similarly, if we had oxygen, okay, now oxygen is an element. What's its standard state or standard state under standard condition? It's a gas, right? It's a diatomic gas. If you provide some energy to that, to this gas over here, again, the molecule will dissociate, and this time we'll get 2 atoms of oxygen, right? So if we have 2 atoms, 2 gaseous atoms of oxygen, then in this case, what's going to be the enthalpy change? Is it going to be the enthalpy change of atomization of oxygen? Or is it going to be twice the enthalpy change of atomization of oxygen? Any suggestion? Hussain?
Sir, twice.
Yes, twice, because we've got 2 moles of the gaseous atoms on the product side. Okay, so this was enthalpy change of atomization. The enthalpy change when 1 mole of a gaseous atom is formed from its elements under standard conditions. Okay, from its element. Okay, can be magnesium, can be oxygen, can be chlorine, can be any element. If we are breaking it down into its standard state, then in that case, we are actually providing it enthalpy change of atomization. All right. Now, if we talk, okay, in this case, we broke oxygen molecule to oxygen atoms. In this case, we actually broke the oxygen-oxygen covalent bonds, okay? Not the intermolecular forces. Again, I'm stressing, it's not the intermolecular forces that have been broken, because the state is the same, but rather it's the oxygen-oxygen covalent bonds that have been broken and giving you 2 oxygen atoms, all right? So if you need to calculate the enthalpy change of this reaction, the enthalpy change of atomization of oxygen, all you need to do is just calculate the bond energy. The bond energy is going to be twice the enthalpy change of atomization of oxygen. The bond energy of oxygen is going to be twice the enthalpy change of oxygen, right? Because this is the energy that we gave to produce 2 atoms, 2 gaseous atoms of oxygen. And so now if we divide the bond energy by 2, we'll get our enthalpy change of atomization of oxygen. So this was enthalpy change of atomization. A quick recap from AS again. Moving on to ionization energy, guys. Remember ionization energy? We did this in great detail. And energy, the enthalpy change when 1 mole of electron is removed from an atom in its gaseous state to form 1 mole of gases, 1 positive ion, right? Or I should rather say it is the energy needed to remove 1 mole of, if for example this is your atom and this is the valence electron, so the energy that I provide to this valence electron, okay, valence is important. In case of ionization energy, it's the valence electron that we are dealing with. Energy that we provide to this valence electron to remove it from this gaseous atom and form, once the electron has been removed, what charge will this gaseous atom attain? It will get a positive charge, okay, to form 1 mole of gaseous 1 positive ion. Okay, this is called ionization energy or enthalpy change of ionization. All right, so this is also a term that you guys need to know for this chapter. Right, so far we've revised 3 enthalpies. We've revised enthalpy change of formation, we've revised enthalpy change of atomization, and we've revised enthalpy change of ionization or ionization energy. Okay, formation is when 1 mole of a compound is formed from its elements under standard conditions in their standard states. Atomization is when 1 mole of gaseous atom is formed from its element under standard conditions. Okay, and ionization energy or enthalpy change of ionization is when 1 mole of electron is removed from 1 mole of gaseous atom to form 1 mole of gaseous 1 positive ion. Okay, so in that case you have your enthalpy change of ionization or ionization energy. Right, now a new term, electron affinity. Electron affinity is actually the reverse of ionization energy. In ionization energy, what we did was we took a gaseous atom, we provided it with some energy, and we removed an electron from it, forming an M positive ion. Right? The enthalpy change associated with this reaction was the enthalpy change of ionization. Electron affinity, on the other hand, is actually the reverse. It is the enthalpy change when 1 mole of a gaseous atom, it gains an electron, it gains 1 mole of electrons to form 1 mole of gaseous 1 minus ions, okay, or 1 mole of univalent negatively charged ion. So the enthalpy change of this reaction is the electron affinity, and in this case, like in case of like ionization energy, electron affinity also has first electron affinity, second electron affinity, and third electron affinity, and so on. Okay, this is called first electron affinity because the product that you get gains a charge of -1 in this case. Okay, its magnitude is 1. Ionization energy in this case was also the first ionization energy because you've removed 1 electron to get a charge of +1. Okay, so this is actually an electron affinity of this reaction. Now, first electron affinity is when 1 mole of electrons, I've written it down over here. Guys, the definition of electron affinity is important, okay? This is asked in A2. Ionization energy is not that frequently asked, but electron affinity, since this is a part of A2 syllabus, so it is asked, and this is the definition that's written over here. Okay, the first electron affinity is when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of univalent negatively charged gaseous ions. Okay, and this is how you're going to represent it in the form of an equation, right? So the first electron affinity in this case of chlorine. Now, second and third electron affinities and so on. Okay, now guys, remember one thing. This first electron affinity is generally exothermic. The reason why it's exothermic is because you are actually adding an electron to an atom, right? Electron is added, and this atom is positively charged, electron is negatively charged. You've actually established an electrostatic force of attraction between the electron and the atom. So this electrostatic force of attraction, the establishment of an electrostatic force of attraction is actually like a bond forming between them, right? This is just like a bond forming. And you guys know that bond forming reactions are generally exothermic reactions, okay? But here's an interesting fact. Second electron affinity is always endothermic. It's never exothermic, it's always endothermic. Any suggestion why? Anyone? Okay, when is a reaction endothermic? When bonds are being formed or when bonds are being broken? Bonds are being formed, right? Bonds forming reaction is endothermic. Now, if bonds are being formed, that would mean No, sorry. I just not formed. Actually, reactions are endothermic when bonds are broken. Okay, you actually provide some energy to break the bonds, to break certain bonds. So now, if you are providing energy to break the bonds, that would mean that the enthalpy change is exothermic. Now, in this case, in case of second electron affinity, what happens is that you already have a negatively charged ion, okay, M-1, and to this negatively charged ion, you are adding an electron, which is also negatively charged. Both of them are negatively charged species, and since they are negatively charged species, since they are like charges, so repulsion occurs between the like charges, right? So in order to overcome this repulsion, we need to provide a large amount of energy. We need to provide energy. So since energy is absorbed in this reaction in order to overcome this repulsion, therefore the second ionization energy is always and always endothermic. Okay guys, did you get this? Why second ionization energy is always endothermic?
Yes, sir.
Okay, moving on. Then finally, A2 stuff. Born-Haber cycle and lattice energy. I'll come to the Born-Haber cycle in a bit. You didn't understand about the first. Okay, just a moment, Hassan, I'll go back. Okay, the first electron affinity over here is when you are adding an electron to an atom, to a gaseous atom. Okay, so now if you are adding an electron to a gaseous atom, that would mean that that electron is establishing an electrostatic force of attraction with the nucleus of that atom, right? This establishment of electrostatic force of attraction is just like bond making, bond forming, right? And since bond forming are all exothermic reaction, that's why this is generally exothermic. Now do you get it? Okay, now moving on. Born-Haber cycle, we'll just come to it after doing lattice energy. Okay, what is lattice energy? Lattice energy is also an enthalpy change. This is something you guys need to know. And by definition, it is the enthalpy change when 1 mole of a solid ionic compound, 1 mole of solid ionic crystalline, this crystalline word is optional though, okay, solid ionic crystalline compound forms from its elements under standard conditions. From its, actually not elements, from its gaseous ions. So moment, not elements. From its gaseous ions under standard conditions. So for example, sodium chloride formation. If you have sodium ions in the gaseous form and you have chloride ions in the gaseous form, they are oppositely charged, right? So obviously attraction will occur in between them and they'll combine together to form sodium chloride solids, 1 mole, right? 1 mole of sodium chloride solid. Enthalpy change of this reaction is going to be the lattice energy of NaCl. Okay, so now what is lattice energy? The enthalpy change when 1 mole of a solid compound, okay, solid has a mark, solid ionic crystalline compound is formed from its gaseous ions under standard conditions. The standard conditions stay the same, 25 degrees Celsius, 1 atmospheric pressure. then the enthalpy change is called the lattice energy of that product, of that compound. Okay, lattice, I've also written the definition over here. It is the enthalpy change when 1 mole of a solid ionic compound is formed from its separate gaseous ions under standard conditions. Okay, and these are a few examples of how lattice energy can be represented. Okay, this is actually L, okay, not C, this is L. Okay, so lithium ion combining with fluoride ions in their gaseous state forming lithium fluoride. Okay, in this case it's going to be the lattice energy of lithium fluoride. And similarly, lattice energy of sodium chloride, this is Cl. Lattice energy of magnesium chloride. Okay, although we have a 2 over here in chlorine, but this doesn't affect our value. This is still the lattice energy of magnesium chloride, because this lattice energy depends upon the magnitude of the product. If we have only 1 mole of this product, then that means that we have only 1 mole of the lattice energy. Okay, and in this case, lattice energy of magnesium chloride. Okay, now guys, an interesting question: is lattice energy gonna be exothermic or endothermic? Any suggestion? Hussain, any suggestion? Endo or exo? We are forming bonds. Yeah.
Exothermic.
Exo. Okay, exo. Why exo?
So bonds are being formed.
Yes, exactly. Bonds are being formed and no bonds are broken. Okay, so if no bonds are broken, that would mean that this is a completely exothermic reaction. Okay, it's a completely exothermic reaction. No energy is being absorbed, but only energy is being released because bonds are formed between the oppositely charged ions. Okay, and the more negative the lattice energy, this is an important statement, guys. The stronger the ionic bonds are, and I can say that the more stable the ionic product is. Okay, the greater its stability. If you guys review your AS again, remember we used to relate the stability with the exothermic reaction. Exothermic reactions generally have more stable products than the endothermic reactions. Reason? Because its products were at a lower energy level. Okay, this was a statement that we used to state during the AS. So guys, over here as well, the more negative means the more exothermic the lattice energy is, the stronger the ionic bonds are, and the more stable the product is. This is actually a concept that has been tested frequently in the past papers. Okay, guys, so you guys should know. This is important. If you didn't get it, so you can ask again. Okay, but this is an important concept. Okay, the more negative the lattice energy, the more stable the product. So in this case, in these 3 equations over here, lithium fluoride, sodium chloride, and magnesium chloride, which of the 3 is most stable? Anyone? Which one of the 3 compounds is the most stable compound? Magnesium chloride. Yes, correct. It's magnesium chloride, because its lattice energy is the most negative. Yeah. All right. Now moving on to the next slide. Oh, before we move on to the next slide, let me clarify what Born-Haber cycle really means. All right. So far, we've, I'll just end this slideshow. Okay, guys, so far we've discussed a few terms, a few actually enthalpy changes from AS. We discussed the enthalpy change of formation. We discussed the enthalpy change of atomization. We also discussed the ionization energy, electron affinity, and finally lattice energy. Now, if we draw out a Hess's cycle that combines all of these terms together, if we draw out a Hess's cycle, you guys remember what Hess's cycle is, right? Hess's cycle is actually a cycle. It is a law of conservation of energy, and it is a relationship of different enthalpy changes of different reactions. Now, Hess's cycle, if we draw out a Hess's cycle that combines or that associates the enthalpy change of formation, the enthalpy change of sometimes the enthalpy change of atomization, enthalpy change of ionization and enthalpy change of electron affinity, basically EA, delta H EA, or electron affinity, and the lattice energy. If we draw out a Hess's cycle that interconnects all these enthalpy changes, such a Hess's cycle is known as a Born-Haber cycle. Okay, so Born-Haber cycle is not anything new for you guys. It's the old Hess's cycle from AS, but it is a Hess's cycle that interconnects all of these different enthalpy changes together, right? And now I'm also going to draw out the Hess's cycle for you guys so that things could get a bit clearer. The definition of Born-Haber cycle is right over here. I've written it down. A Born-Haber cycle is a cycle, a Hess's cycle that gives relationship between, okay, I've missed out the term Hess's, but you could add it over here. It is a Hess's cycle that gives a relationship between enthalpy change of formation of an ionic solid crystalline compound and the enthalpy changes in the stages of its formation. All right. So basically, enthalpy change of formation, this is something that we've already discussed. Okay. And I told you that all the different enthalpies, so it's the delta HF that we are talking about over there, and all the different enthalpy changes that are associated in its formation. Basically these, okay, over here. I'll shift to the whiteboard now. Right, so let's draw out a Born-Haber cycle of sodium chloride. Sodium solid, when combines with chlorine gas, it forms NaCl solid, right? Let's balance it out. Half moles of chlorine gas. Guys, what is going to be the enthalpy change of this reaction? Anyone? Out of the 5 that I just listed, enthalpy change of formation, enthalpy change of atomization, etc. It's gonna be enthalpy change of formation. Yes, correct. And enthalpy change of formation of sodium chloride, to be more specific. All right. This is the enthalpy change of formation of sodium chloride. And what about the lattice energy of sodium chloride? If I write down sodium ions in the gaseous state, if combined with chloride ions in the gaseous state to form sodium chloride solid state, 1 mole of sodium chloride in the solid state, then the enthalpy change of this reaction is going to be the enthalpy change of lattice, basically the lattice energy, right? And this is something that you've done in A2. Okay, this is new for you guys. This is from AS, but this is from A2, right? And the definition of lattice energy is asked in A2 as well, okay? So the enthalpy change when 1 mole of a solid ionic crystalline compound is formed from its gaseous ions under standard conditions, okay? And you guys know what standard conditions are very well. 25 degrees Celsius, 1 atmospheric pressure. And 1 mole per dm cube concentration as well in case of solutions, all right? So this is lattice energy. Now, if I ask you, what's the standard state of sodium under standard conditions? So you guys are gonna answer me that it's a solid, right? Okay, if it's a solid, then if I heat it and form sodium gaseous atoms, what's going to be the enthalpy change of this reaction? Is it going to be the enthalpy change of atomization of sodium? Right? Because I'm getting 1 mole of gaseous sodium ions, so sodium atoms from its element under standard conditions, okay, in its standard state. This is enthalpy change of atomization of sodium. Now, if I remove an electron from sodium, I'll get sodium positive gaseous ions, okay? And the enthalpy change of this reaction is actually gonna be the first ionization energy of sodium, right? Agreed, guys? Yahan tak koi issue? Any issue so far? Okay, now, we've got our gaseous sodium ion. We've got one of our reactants for this reaction, for this equation over here. we are actually trying to get this other reactant now. We've got our first reactant, the sodium gaseous ion, right over here. Okay, this is what we needed to generate from the standard sodium. Okay, now we need to generate the other reactant. Chlorine, if we start out from its standard state, it's a gas under standard conditions, right? It will gain electron from sodium, okay? And if it gains electron from sodium, it will form chloride ions. Let me take half moles of chlorine molecule, okay? So now the equation is also balanced. So 1/2 moles of chlorine molecule will gain 1 mole of electron to form 1 mole of chloride gaseous ion. The enthalpy change of this reaction, what's going to be the enthalpy change of this reaction, guys? Oh, okay, wait. I just missed out a step. Before we go over there, first we need to atomize the chlorine molecule, okay? So now to atomize the chlorine molecule, we'll get 2 chlorine atoms in the gaseous state, right? The enthalpy change of atomization of chlorine. But since we've got 2 chlorine atoms, this is going to be twice the enthalpy change of atomization of chlorine, okay? Now, once we have twice the enthalpy change of atomization of chlorine, or to keep stuff simple, okay, just assume this is twice the enthalpy. Okay, let's keep stuff simple. Let's not consider this twice. Let's divide the entire equation by 2, okay? So dividing the entire equation by 2 would mean that the equation can be balanced this way too, right? In this case, now the enthalpy change of this reaction is going to be the enthalpy change of atomization of the chlorine atoms, right? Now, once we've got our gaseous chlorine atoms, what's the next step? In case of sodium, to form positive ions, we removed an electron from sodium, right? In case of chlorine, to form a negative ion, chlorine has to gain an electron. And once it gains the electron, it forms a chloride ion in its gaseous state, right? In this case, what's going to be the enthalpy change of this reaction? Again, this is something new for you guys. This is A2 stuff. This is the electron affinity. The first electron affinity of chlorine. Yes. Okay, this is the first electron affinity of chlorine to form 1 mole of chloride ions. Now we've got chloride ions, we've got sodium ions. If we combine the two of them, we combine sodium and chloride, we'll get sodium chloride. Solid. Okay, and if we get solid sodium chloride from gaseous ions, then what do you guys think? What do you guys think? Isn't this the lattice energy of sodium chloride? This is the lattice energy of sodium chloride. When 1 mole of a solid crystalline compound is formed from its gaseous ions under standard conditions, okay? So this is actually the pathway through which we get our crystalline solid associating the lattice energy. Okay, just a moment, I'll get. So associating the lattice energy. So now all we need to do is just combine all these pathways in a single cycle to form a Born-Haber cycle. Okay, so this was the pathway through which we get our sodium chloride finally from the gaseous ions. Now, to illustrate this in a Born-Haber cycle, first of all, what you do is take sodium in its standard state, you take chlorine gas in its standard state, and take exactly the same moles that you need to form 1 mole of the compound, okay? So sodium solid combines with 1/2 moles of chlorine gas, okay? You show them by a horizontal line. When they both combine together, they form sodium chloride. Another horizontal line over here. And you label this line with sodium chloride solid, okay? Now the enthalpy change, this arrow over here, this is actually the same arrow that you used to use in the Hess cycle, okay? This is also going to be labeled with the enthalpy changes, but in this case, it's going to be a bit more precise. This case is going to be the enthalpy change of formation of sodium chloride, Okay, so now, and why is this arrow facing downwards? This is facing downwards because the sodium combining with chlorine forming sodium chloride. This is actually an overall exothermic reaction. Okay, so for exothermic reactions in Born-Haber cycles, the arrows point downwards. This is a point to remember. Now, the first step is convert this. What's going to happen is that this sodium solid, first it will atomize. Okay, it will atomize to form sodium gaseous atoms. Okay, so once sodium atomizes, the enthalpy change of this reaction is going to be enthalpy change of atomization of sodium and standard, right? And this is something you have to label in Born-Haber cycle, and you have to draw another level over here as well and copy the chlorine as it is, because we've done nothing to chlorine yet in its gaseous state. Then once sodium has been atomized, then we are going to provide more energy to sodium so that it could lose its valence electron and transfer it to chlorine. Okay, transfer its electron to chlorine. So, but before we do that, just 1 minute. All right. Simultaneously, you can label over here as well. You can atomize the chlorine molecule as well. Okay, or you could just draw a separate arrow for it. But to save space and make it a bit neater, you can draw another simultaneous arrow over here, labeling enthalpy change of atomization of chlorine. Okay, and you'll get gaseous chlorine atoms as well. So you've actually provided energy to sodium solid and chlorine gas, forming their corresponding atoms, and 1 mole of their atoms have been formed, so their enthalpy changes are actually 1 moles of each of them. Okay, now once you've got the enthalpy change of atomization of chlorine and enthalpy change of atomization of sodium, now you are going to provide more energy to this sodium so that it could lose its electron. So now, if the sodium loses its electron, it will form sodium positive ions. Okay, and this is the electron over here. Plus, you'll have the chlorine gases atoms side by side. Okay, sodium has lost its electron. So what's going to be the enthalpy change of this reaction? And guys, do you notice something? These arrows are all facing upwards. Why are they facing upwards? Because these are all endothermic reactions. We are actually providing energy to convert it from solid to gas, and then we are providing more energy to remove the electron from this sodium to form sodium positive ions. Okay, now the enthalpy change of this reaction is going to be the first IE, or the first ionization energy of Na, of sodium. Okay, this is exactly how you're going to label it. Now once you've got these products, extend this a bit to the right. I told you guys this electron is going to be accepted by this chlorine atom, gaseous atom actually. This is going to be the electron affinity, but this electron affinity is the first electron affinity, and I told you that first electron affinity is generally exothermic. So chlorine gaseous atom will accept 1 electron, and to show the exothermic reaction, the arrow will point downwards this time. And the products that you'll have at the end of this arrow are going to be the sodium gaseous ions as it is, along with the chloride gaseous ions. And you've got the enthalpy change of this arrow is going to be the electron affinity, or first electron affinity of chlorine. Okay, forming chloride ions. Now once you've got your reactants that you need for lattice energy, and you guys already know that lattice energy is a highly exothermic reaction, or highly exothermic, lattice energy is highly exothermic. Sodium gaseous ions combine with chloride gaseous ions to form sodium chloride. It's going to be a highly exothermic reaction, and you'll get your sodium chloride. Enthalpy change of this reaction is going to be delta H of lattice. Why enthalpy change of lattice? Because you are forming 1 mole of the compound, solid crystalline ionic compound from its gaseous ions under standard conditions. Okay, so this is how you form a complete Hess's cycle. Okay, this is how the Hess's cycle looks like. Okay, any questions so far? Okay. Or Born-Haber cycle. Actually, Born-Haber cycle is a specialized Hess's cycle that is used to calculate the lattice energy of a solid ionic crystalline compound. Okay, so Born-Haber cycle in reality is actually a Hess's cycle, but a more extended form of a Hess's cycle. Born-Haber cycle is a Hess's cycle as well. Is an extended Hess's cycle. So this is a cycle, or the energy, this is a cycle. This is okay, this is actually a Hess's cycle and an energy level diagram. This cannot be specifically called an energy level diagram, but yeah, you can get a rough idea from it of the energy levels, because each of this horizontal line represents a different energy level, okay, showing that each compound where its energy lies. But this is, yeah, you can call it an energy level diagram as well, but it is a specialized Hess's cycle. Okay, any more questions, guys? Should I continue? All right, I'll continue then. Okay, so what if we use magnesium? Yeah, magnesium, we are gonna come to that example too. We are gonna form magnesium. In case of magnesium, we are gonna first form magnesium positive ions. Okay, that's gonna be the first IE of magnesium, and then we are gonna form magnesium 2 positive ions. That's gonna be a second IE of magnesium. Okay, the first and second, and so you're gonna show you can show it by 2 arrows or just a single arrow, but that arrow is gonna be labeled as first plus second IE of magnesium. Okay, in case of magnesium. But we are gonna do an example of magnesium as well. Magnesium chloride as a cycle. Anyways, now a quick recap of the steps which you guys need to remember. Okay, first you have your elements in the standard state. They combine and form your product, your 1 mole of compound, and this is called the enthalpy change of formation of that compound. Okay, now once you have the enthalpy change of formation of that compound, this is delta HF. Okay, then this solid sodium compound will be first atomized, and the other reactant will also, sodium is not a compound, it's an element, sorry, sodium element and chlorine element, they both will be atomized first. Okay, so the first step is atomization, then the second step is ionization, and third step is electron affinity, and fourth step is lattice energy. Fifth is this delta HF. Okay, now guys, since I told you that this has a cycle, so we can apply the same law of conservation of energy on this Born-Haber cycle as well that we used to apply in AS. Okay, I'm gonna do it right over here, and it's pretty simple. Oh, come on. Okay. Right, first of all, this enthalpy change of formation, it is pointing downwards, right? The enthalpy change of formation of NaCl is on one side, okay? This enthalpy change of formation of NaCl is actually equal to, this is forming your NaCl, right? This is forming NaCl. This is one way you can form NaCl, or you could go all the way around to form NaCl again. Hess's law says that the change in energy is the same for a particular reaction, whether the reaction takes place in a single step or a series of steps, right? So now that means that this enthalpy change over here is gonna be equal to the sum of all those enthalpy changes which lead to NaCl. Okay, so this means that enthalpy change of formation of sodium chloride is going to be equal to the enthalpy change of atomization of sodium plus the enthalpy change of atomization of chlorine plus the first IE of sodium plus the first electron affinity of chlorine and plus the lattice energy of sodium chloride. So this is an equation that you form following the Hess's law. Okay, that enthalpy change of formation is equal to the enthalpy changes of all of those steps, right? So this equation is very important. Okay, not just for this Born-Haber cycle, but it can be applied everywhere on any Born-Haber cycle, and there have been quite frequent questions testing this concept and testing your ability to form this equation, and then they sometimes give you the enthalpy, some data, and then they ask you to calculate the lattice energy. If we make the lattice energy the subject from this equation, we can easily calculate the lattice energy. So hence prove that this has a cycle this Born-Haber cycle is a specialized as a cycle that is used to calculate this lattice energy of a particular solid crystalline compound. Okay. Now let's take another example of magnesium chloride, and in fact the last example. Okay, magnesium solid combining with chlorine gas forms magnesium chloride solid. Okay, the enthalpy change of this reaction is going to be the enthalpy change of formation of magnesium chloride. All you guys need to do is just construct a Born-Haber cycle now. So the basics are the same. Okay, I'll go take a few, please. Magnesium solid combining with chlorine gas. Okay. Enthalpy change of formation of magnesium chloride is also exothermic. Okay. And guys, don't worry, it's gonna be mentioned in the paper whether the reaction is exo or endothermic. Okay. Generally, the enthalpy change of formation that they give you is exothermic. Okay, because the product of exothermic reactions is quite stable. Okay, so you don't need to worry about this. This data will be given to you. Anyways, magnesium reacting with chlorine forms magnesium chloride solid. Okay, so this is the first pathway, and the second pathway is now you need to convert this magnesium solid and chlorine gas into atoms first. Okay, you can show them by a single arrow as well. Okay, so but labeling must be correct. Enthalpy change of atomization of magnesium plus enthalpy change of atomization of chlorine. Okay, and if they've asked you the standard, so the standard sign must also be labeled over here. When both of them combine together, when they both of them are atomized, they'll form magnesium atom. Magnesium gaseous atom and chlorine 2 atoms of chlorine. Okay, you've got 2 atoms of chlorine, so this is actually going to be twice the enthalpy change of atomization of chlorine. This is something you guys should be careful about. Okay, you are getting 2 moles of chlorine atoms over here. Now once you've got your chlorine atoms, the next step is removal of electrons from the magnesium. Okay, now magnesium chloride means, in magnesium chloride, if you guys look at magnesium chloride, the charge of magnesium is +2. This means that magnesium has lost 2 electrons. So this means that both first ionization energy will form magnesium positive ion, and then followed by second ionization energy will form magnesium 2 positive ion. You can show it using 2 arrows, okay? Each one of them labeled as first and second IE, or you could just do this. You could just convert this magnesium gaseous atom to magnesium 2 positive ion directly. Okay. In the gaseous state, of course, chlorine atoms are copied as it is. And you can label this arrow as the first plus second IE of magnesium. Okay. This would be a better way of labeling because it will occupy less space. Okay, generally not much space is given to draw the Born-Haber cycle. So you have to kind of squeeze stuff in. So this is going to be a better way of labeling it. Okay. Now once you've, and of course the electrons that magnesium has lost. Okay. Now once you've got the electrons that the magnesium has lost, these electrons are going to be gained by chlorine. But guys, remember, this is not the second ionization and second electron affinity of chlorine. This is not the second electron affinity of chlorine. This is actually going to be each of the chlorine atom gaining one electron. This would mean that this is going to be twice the first ionization, first electron affinity of chlorine. Okay. Now I'll explain what I just said. Just a moment. Two electrons gained by two chlorine atoms will form two chloride ions, right? Magnesium ions, magnesium 2 positive ions in the gaseous form, and two chloride ions in the gaseous form. So you've gotten two chloride ions, so that's why this is going to be twice the electron affinity of chlorine, because each of the chlorine atom will form one chloride ion, and each of the chloride ion is going to be it will form two chloride ions. So therefore, this is going to be twice the first electron affinity of the chlorine atoms. Okay, it would have been the second electron affinity of chlorine if the chlorine would have gotten a charge of -2, but that isn't the case over here, right? Since the chlorine has a charge of -1, therefore this is going to be twice the electron affinity of chlorine, right? So therefore this is exothermic. This remains exothermic. This is not endothermic. Okay. Now once you've got magnesium chloride, what do you do next? Sorry, you've got magnesium ions in the gaseous state, you've got chloride ions in the gaseous state. They'll combine together to form magnesium chloride solid. Again, this is fitting the definition of lattice energy. So the enthalpy change of lattice, okay, of magnesium chloride, you can label that as well. So this is again a Born-Haber cycle that you've made for magnesium chloride. Okay, and again the same Hess's law can be applied over here as well. Okay, let's apply the Hess's law as well. Okay, so this step is equal to the remaining steps. So the enthalpy change of formation of magnesium chloride is equal to enthalpy change of atomization of magnesium, okay, right over here, plus twice of enthalpy change of atomization of chlorine. And yeah, guys, don't forget to mention this standard sign over here, plus first and second ionization energy of magnesium, plus electron affinities, twice the electron affinities of chlorine, and plus the lattice energy. Right, so this is the Hess's law equation that you get from this Born-Haber cycle. Hassan, is your confusion clear? Okay, of the magnesium 2 positive? All right, cool. So any question in this Born-Haber cycle? Guys, again, the basic steps stay the same, okay? You form an equation for formation, you form equations for atomization first, then you remove electron, that is ionization, and then you gain electron, that is electron affinity, and then you form your lattice energy products finally. Okay, now let me check what do we have next.